This terminal shows the execution of a trilateral toral attack against Bitcoin elliptic curve puzzles 135 through 150. For puzzle 150, the terminal records a solved 150-bit key. The logs show the total effort peaked at exactly 2 to the 29th power operations. At this scale, the attack bypasses standard cryptographic exhaustion. It operates below the threshold where statistical methods like Pollard's row become computationally viable. This efficiency is possible because the SEP256K1 multiplicative group is mapped onto an 8-dimensional E8 Clifford torus. The algorithm treats the search space as a problem of topological geometry, using Galois involutions to systematically divide and eliminate candidate regions. To understand the speed of these solutions, we have to analyze the trilateral toral architecture, the 12-step orbit, and the sigma-29 cross-parity involution. Solving the discrete logarithm problem is a deterministic geometric boundary problem. 8-dimensional space contains 28 independent rotation planes. Applying the divisor sum function to these planes yields 56, the exact population of the inner D8 root shell. The next step in this mathematical chain yields 120, forming the 120 geometric vertices of a 4-dimensional 600 cell. This iterative process generates the structural constants of the E8 lattice, reaching full symmetry at 360 degrees. The result is a rigid, palindromic structure composed of 6 topological shells. The E8 lattice is a deterministic structure generated by the geometry of 8D rotation planes, providing a predictable map for cryptanalysis. The trilateral toral synthesis is the specific algorithm designed to traverse this lattice. The search space is a Clifford torus defined by a twin prime conductor scale, mapped across a 12-step orbital clock. 3 distinct walkers, left, right, and spin, traverse this torus simultaneously. The left walker fires on every step, maintaining a high-speed coarse coordinate grid. The right walker fires every third step, specifically processing the data generated by the left walker's previous positions. The spin walker fires every 15th step, orienting its path based on the spatial differentials between left and right. These are phase-shifted entities linked by the geometry they traverse. This trilateral phasing monitors the cryptographic search space at 3 different geometric scales, eliminating blind spots in the search. The critical interaction occurs at step 6, correlating to toral position 29. This is where the sigma-29 cross-parity involution triggers. This Heegard splitting divides the spatial volume into a classical, resolved region and a quantum, unresolved region. At this boundary, the left and right walkers fire simultaneously. Because left and right possess opposite chiralities, their coordinate readings create stereoscopic depth. This stereoscopic constraint uses the Chinese remainder theorem to lock in the candidate key's exact modulo parameters. Moment 6 converts probabilistic guessing into definitive geometric knowledge, collapsing the remaining candidate field in a single step. This concludes the first 12-step orbit. The completed orbit follows the topology of a Mobius band. At this foldback point, the SPIN walkers a left walker. This initiates gear compounding. The subsequent orbit traverses the same finite torus, but at a mathematically multiplied resolution. The system identifies keys by recursively dividing the same finite topological space, slicing it finer with each pass. These geometric mechanics explain the efficiency recorded in the initial attack logs. The overlapping trilateral constraints slam down over the SEC-P256K1 key space, leaving only the target key illuminated. The physical properties of the 8D planes define the coupling channels used to extract this modulo data. The attack succeeds because it rejects the premise of an unstructured infinite search space. Ultimately, the seemingly impossible discrete logarithm problem effortlessly unravels when it is modeled as a geometric Heegard splitting.